So these are the various methods which are provided with strings. Consider the example of strlen. Basically, it returns the length of the string. Then you have a putc function in which it replaces the ith character in a string with a given integer value. Then you have a getC function which actually returns the ASCII code of an ith character in a string. Then you have two upper, two lower, compare, I compare, substr string, a2i, a2 real, I2a, very much like C++. But yeah, the whole description is available in your language reference manual. So you can actually go get to the language reference manual and find the detail of each and every function of string. Okay, let's come to arrays. Arrays are a really important concept in System Verilog, because whenever you want to demonstrate a memory, or you want to demonstrate a RAM, so arrays are used, because you can have a single dimension memory space or a double dimensional memory space, in fact 3 dimension, 4 dimension of memory space as and when required. So System Verilog provides a very handful use of arrays particularly, and they are really handy when you are dealing with various data and various different sizes of data. So in this case, you have basically an array is a collection of variables of the same type. Then you have then in this case you have an equally sized data types, in which data element should be equally sized. Like for example, if it is a byte array, then all the elements are of size bytes. If you have an integer array, then every element of this array is of 32 bits, and henceforth. So basically that is one kind of limitation which this array provides. Then you can have a packed array, and then an unpacked array. Packed array generally means that the memory space which is being allocated to each element is contiguous as a whole. So for example, if you have a packed array I'll come to the example in the next slide. So then the whole memory is allocated in a contiguous way. Then you have an unpacked array. Then System Verilog accepts a single number as you do it in C++, as compared to Verilog, where you have to give a range of a variable, like 0 size minus 0 down to size minus 1, or size minus 1 down to 0, whichever Indianness you want to consider. Okay, so in case of packed and unpacked array, you have a bit a 3 down to 0. So in this case you can see that there is an unused, and these memory locations are unused basically, and they are the 3 bits that this array A is of 4 is of 4 memory location, each occupying a single bit. So A0, A1, A2, A3 are all of a single bit. Now this is a perfect example of an unpacked array. Then the packed arrays, in this case all the memory location are packed. You can see that the first location is P0, then the second, then the third, then the fourth, and then the remaining is unused. It again depends upon the simulator by which you are compiling your System Verilog code. Consider this example of memory. In this, basically you have 16 rows, and these 16 okay, so consider the example of bit 515 down to 0, memory 1023 down to 0. In this refers to the packed location, this refers to the unpacked location, and this refers to the packed location. So this basically changes to a memory in which you have 16 rows, and each row is basically 1024 bit wide. So in consider this is as a bit, so this memory is of 16 KB size, kilobit size, and this is the way you can actually instantiate value to each location. Memory I is basically minus of memory I, and henceforth. So this is a block in which you are using an always at, and with this each edge, this changing value of VCMD, the wave frame is getting values or opposite value of it. Okay. Okay, let's come to an important concept of an associative arrays. So associative arrays are really important in cases when the size of location, when the size of memory which the user want to use is not known basically. So consider an example of a memory verification controller in which you have like 512 MB of data. Now if you are using a normal array, then at the time 0 only you have to allocate 512 MB of memory, which this is very costly as if you consider the system resources. So it's a very costly system resource, costly as compared for the system resources, and hence arrays use is not recommended. So better is, and you also know that, and it is also known that the in memory all address locations are not actually used at a single go. So as and when required, if a particular end is writing or reading from the memory, that particular location need to be allocated first. So for example, if you make an associative array in this case, then you can have whichever address you want to be allocated first, that address can be allocated using the associative arrays. And hence in cases of memory or in cases of RAM, which is basically very high, which is high resource consuming, it's better to instantiate an associative array. And as and when required, you can delete an element or you can add an element, and the memory location is on the fly. So associative array is very potent in those scenarios. So um, in case of associative array, it is very useful when the size of the collection is unknown. As I said, they do not have any storage allocation until it is used. Index expression is not restricted to integer expression, but can be of any type. As we will see in the next slide, it can be of as string, it can be as classes, it can be a wildcard as well, it can be integer as well. So that is one thing. Associative arrays can be considered as lookup tables or hash tables or maps in software terms, but yeah, they are really helpful, and these are the methods which are provided in the system language reference manual, and you can actually manipulate all the data in associative arrays. So consider the syntax. So it's basically a data type which can be int, struct, union, or a shortened or a byte or a logic or a reg, anything. Then you give a name of your associative array. Here I have given the name array ID, and then this index type. Index type can be, again as I told, it can be an integer, it can be a string, it can be a class object, it can be a wildcard. So anything can be the index type. So but once the index is being used, that index has to be constant throughout the use of associative arrays. Like for example, if the index uses an int, so it's restrict that index expression to that particular type. Okay, so in this case of integer array, associative arrays can be of integer or integral index, in this case the ordering is numerical. It can be of any integer expression, like you can do a multiplication of two index, or you can do addition of two index, whatever is required. But indices are signed here. They are signed, and that is to be taken care of. And a good example is int array name integer. Okay, now in the second is the string index. For example, you are maintaining a student's directory and you want to have an associative array based on a student name. So string index is really helpful in that case. So for example, if you want to add a collection, add to the data collection of students, so you need to have an index as Ram, Shyam, or anything. Or so in this case, ordering is lexicographic, and index can be string or string literals. And this is an example, again, int array name string. Now class index is basically, it also take care of the structs. So any struct can also be part of an of a index. So null index is also valid. Ordering is deterministic, but it is arbitrary. And index can be of any type, can be of derived type as well, can be a struct, union, anything. Then coming to while character index, so this is one thing which is mostly used basically. So indices are unsigned in this case, and index expressions are self-determined. And if you are using a string literal index, then it is autocast to a bit vector of equivalent size. Then ordering is numerical in this case. So example is int array name star. So let's come up to the example of example of associative arrays. In this you have a module integer associative array, then you define a variable integer as associative memory, and the indexing here is another integer. Now you can see that in this case the memory is instantiated with value 100, and only in this case one memory location is allocated memory, that is 100th location, and 0 to 99 is not being allocated. So you can see a very efficient use of memory in case of associative arrays. So you have added an at element 100 a value of 101, then you display it. Then at location 1 you give value of 100, and then you are displaying it every now and then. Then you have instantiated value at 50, then 256, and then you are basically calculating the print size of the array. Then you are displaying what are the whether this array has an element at this num location or not. Then you see that if the memory first is correct or not, then you can say that value of at first index is 1. So by this use of associative array methods and indexing, you can actually do a hell lot of operations, and is very helpful in verification domain. Now let's come to a different kind of data collection thing, that is queues. So intrinsically queues have a sequencing feature in this. So by any queue you can refer it as a last in first out or a first in first out queue, but in all the queues you have this intrinsic quality of sequencing. Now this is very helpful in the case when you have an incoming data stream and you want to maintain the order of an incoming data stream, and you are sending it to some other location where you can actually have that order in which it came, and display it at the console in the order in which it came. So in the case of queues, it's basically a variable size and it's an ordered collection of homogeneous item. So ordinal number represents the actual position of each element in the queue. For example, if you are writing queue 0th location, then it will represent the first element, and if you are using $, then it is representing the last element of the queue. So this is also very important. So there are various methods to access the queues. As you can see that there's an insert, there's a delete, then there's a pop front, pop back, push front, push back. Now you can see that there are basically two functions, both from the front and at the back as well, and this helps to modify the nature of the queue, whether you want a last in first out or a first in first out. So this is very helpful in that case. Size, by the help of size you can basically get the size of get the present size of the array of the queue basically. Okay, now this is a perfect example of a queue in which there is a module queue data, and there are at the first go you are basically assigning 4 values to a queue, and inside the initial begin you are actually first printing the print queue. So in this case at the first go you will have 0 1 2 3 4. Okay, then you have added 5 comma q. Now this is this has to be taken very carefully, that this is basically a concatenation. So in this case what happens is that the whole queue is shifted to one is right shifted to one location, and 5 is basically added to the first location. So I'll come to the output, what how the queue is seen now. Then you are using basically print queue. So the print queue, as you can see, it's 501234. So you can see the queue is 501234. Okay, then you are using a queue dot push front. Then you are so this will actually add 6. Then you are using a queue dot push back at 7, so this will add 7 to the end of the queue. Then you are displaying it. Then you are inserting queue dot insert 4,8. So at the fourth location 8 will be inserted. Here 4 is the index and 8 is the value. And then you are using pop functions, a different version of pop, like pop front and pop back, where basically you are assigning values to I, the first element of the queue and the last element of the queue. The print queue just iterate over the queue size and prints all the value of inside the queue at different location. So as has been said before, the first will this is the original queue which we had 0 1 2 3 4. Then we have this 5 0 1 2 3 4 after the concatenation step. Then 6 was added by using push front. So 6 would be now pushed to 0th location, and the whole 5 0 1 2 3 4 has been shifted towards right. Then 7 was added with the help of push back, and it occupied the space of 8th location. Now there was a function which was called as insert, and at the 4th location 8 was inserted. So it was 0 1 2 3 4. So 4th location 8 was inserted. Then popped. Then the element was popped, and you can see the size of the queue is reducing slowly and slowly. So this completes the excuse me. So this completes the presentation on queue. Now, basically, in case of system Verilog, the casting is very important concept, because system Verilog is very strictly typed language. You cannot instantiate int value to a shortened variable, or a shortened value to an int variable. If you try to do that, the compiler will generate an error, and you have to do some casting in this case. So for example, if you are using if you have a value 2.0 into 3.0, then you have to use a static cast. This is basically a static cast. This is also basically a static cast. So a good amount of care has to be taken care of if you are basically dealing with type convergence in system Verilog. Then a good example of dynamic casting can be seen is, for example, when you are dealing with enums. Enums, for example, in this case, the color is red, blue, green, yellow, white, and black. And if you try to do a dollar cast operation on this color, then 2 plus 3 is 5. So 0, 1, 2, 3, 4, 5. So this color will have black. Okay. So let's see. Let's see what is the example of cast errors. So consider this example in which the color is an enum variable, and only red, blue, green are being associated with this color. And in the initial begin block, you try to dynamic cast a variable d with c plus 10. Now you can see that it is beyond this 3 locations. So in this case, the dynamic cast fails. In this case as well, the enum method, again you have red, blue, green, and since you are doing a c plus 1, so this is an illegal assignment, because you are not doing a dynamic cast here. So d is also a color and c is also color, but c is you are doing an integer operation here. So this will be taken care separately, and it is not automatically type converted to an enum. Hence this it says an illegal assignment. Now system Verilog provides a good combination of C and Verilog operators, you can see that there are lots of operations like binary, unary. Then you have logical, relational, then shift operations. So you can see that there's a complete list of operators in system Verilog. So there are relational operators, there are plus plus minus minus operators, then there are stream operators and concatenation operators. These are all taken directly from Verilog and being used here. The unary increment and decrement operators are taken from C. So with these operations, it really is helpful for the verification engineers to basically deal with various kind of data types and various kind of operations. So incorporating these operators has been particularly boon for the different kind of verification environment to create and to execute. Now let's come to looping statements in system Verilog. As I've already told, these were the prerequisites. I'm adding only for each and loop control. So if else statement, case statement, repeat loop, for loop, while loop, do while loop, case statements. So these all must be taken care in Verilog, and they are, as it is, they are used in system Verilog as well. Two other kind of looping statements are the for each loop and the loop control. So in case of for each, what it does is that it basically iterate over a particular kind of an element. So consider an example of a fixed array of ith location of it's just a single dimensional array, and this value I ranges from 0 to 9. So if you do this for each fixed array I dollar display fixed array E. So what will it do is it will iterate over whatever possible values of I and will display, and it will print those values. So in our case, if it is the range is 0 to 9, then it will come from 0 and till 9th location it will print all the values. So this is a very this for each statement is very helpful in the cases when you want to debug your state or debug your test benches whether the array is being initialized with proper values or not. So in those scenarios, for each has been very useful. Then loop control, the break and continue statement, these are also are exactly taken from C statements and the Verilog statement.